In the last lecture, I give you some mathematical formalism of the homogeneous nucleation, how a solid nucleus can form from a liquid, and in that case how we can deal with in thermodynamical manner. Now, as I said in the last part of my last lecture that whenever a solid phase forms out of a solid or inside a solid rather, like a product solid phase forming inside a parent solid phase, there is a extra aspects we need to consider. The extra thing is the straining of the parent phase and how we can deal with it. That is what we are going to see it now. As you know, we can simply write down the equation in terms of free energies again, but strain basically is a volume energy term. Strain is always proportional to the volume of a surrounding parent phase. Okay, so let me go back and explain it in detailed manner. Suppose if I have a solid, is a complete solid S1, and I form or the system forms a new solid S2, okay, inside S1, and so therefore, as a solid phase is forming out from another solid phase, the densities of these two solids may not be equal. Why? Because density depends on how the atoms are packed, that means density depends on the crystal structure of these two phases. So, as the densities may not be equal, if it is equal that is fine, it may not be equal, then what will happen? Because of these density difference there is a volume change, that means volume of S2 which is formed out of S1 may be higher, may be lower, does not matter, there will be volume change. So, because of volume change there will be elastic stress acting at the interface, and this elastic stress will lead to straining of the solid S1. So, therefore, this must be taken into consider. How we can take into consider? We can always assume the volume energy term has two parts, one which is a chemical free energy term and another one is basically strain free energy term. Okay. What is chemical free energy term? Chemical free energy is the free energy because of the difference in the structure of these two solid phases, okay, and chemistry. Okay, that is the chemical part. Basically it is a chemistry part. That is we have seen. If I plot the free energies, bulk free energies of these two phases S1 and S2, the difference of these two, okay, difference of these two phases will be, difference of these two free energies will be equal to the chemical part. So, if I say S2 and S1, this is the transformation temperature, as you clearly see, as our transformation temperature S2 is more stable and below S1 is more stable, correct. So, therefore, this is S2 and this is S1 free energy curves, or rather I can write down GS2, GS1. So, the difference chemical free energy is nothing but this difference between the two free energy curves. Okay. But strain free energy is also a volumetric term that must be considered, that is also proportional to the volume. So, what I can write down? I can write down this is equal to 4 pi RQ, which is the volume total free energy, this must be equal to volume rather plus basically this multiplied by G volume CH. I am writing down small g value, small g, and this is, that is what we can write down. Okay. So, these are the values of the free energy per unit volume, remember, that is why this is written G volume. Now, we can do the same maths, we can always write down this as a negative because this value is negative as you see here, but the strain free energy term is always positive. So, we can do the same mathematics again. The total free energy is equal to delta G V plus delta G because of the surface energy. So, that is the surface energy term. So, I can write down interface energy term. So, I can write down this as 4/3 pi r cube minus G V C H plus G V strain plus 4 pi r square gamma S L. That is my total free energy system. So, now is simple. Now, actually to find out at r is equal to r star, at what is the d g t by g r is equal to 0. Okay. So, one can simply do the maths. It is basically it will come same thing. So, r star will be minus twice gamma S L G V minus G S C H, sorry, this is strain. What is actually happening is that because of the presence of the strain energy, total free energy of the system, available free energy of the system is getting reduced. This is the total free energy available to the system that is getting reduced by the free energy because of the strain. So, therefore, R star value will increase. That means, the critical nuclear size will be higher when you have a strain in the matrix. As you see, if this value is going down, R star will increase, correct. So, that is the main thing in a solid. Therefore, in a solid to solid transformations, critical nuclei or critical size nuclei embryo rather, which will become nucleus later on, size is bigger than solid to liquid to solid transformation. That is the major conclusion you can draw here. And this is very important because we will see in our examples, means in our different types of phase solid to solid transformations, that this is a strong aspect. Strain will be present inherently in many of the phase solid to solid phase transformations. Similarly, one can calculate G star, again G star is also delta G star, nothing will change much in the numerator, but this one will change, G V C H minus G V strain whole square. Okay, that is how it will change, nothing else will change. So, therefore, again the critical value, that is height, will also decrease because this has decreased. You see here, if this will be solid solid, sorry, not liquid, gamma solid solid, or rather gamma S1 S2, and because this value is getting reduced. So, therefore, delta G will increase again here also, the critical barrier will increase. So, these are the things happens when you transform something from solid to solid. Remember, the most of the transformations which we will study in our case is basically solid to solid. So, therefore, if you really want to do the mathematics properly, you need to calculate what is this free energy change because of the strain, and this free energy can be calculated depending on different types of interfaces. If the interface is coherent, there is no strain energy. There will be complete coherence, there will be no strain energy, but if interface is like a coherency strain is involved, coherency strain means the atomic bonds are little bit distorted, but still the atoms are perfectly bonded with each other, but the bonds are angles are distorted, this will lead to strain. Or you can also have a permanent strain because of dislocation. Dislocations can be formed at the interface to create a semi-coherent interface that can lead to permanent strain. Or in case of incoherent interfaces, strain energy is pretty high because there are lot of distortion of the atomic bonds of the interfaces. So, this value is going to change depending on that, the type of interface is developed. As you can clearly see, the nucleation of the phase is strongly dependent on the type of interfaces we have in the solid solid. So, we can actually take case by case, that is there in the book, basically the second book is there, many examples are given. okay, where you can, by Professor Jena and Professor Chaturvedi, the book Phase Transformations in Materials. There are a lot of examples given of how to take care of this strain part to calculate the free energy change, both the chemical free energy as well as strain free energy change, how to calculate. There are a lot of examples are given. In case you have the book, you can actually solve these problems and get a fair amount of idea how to take care of different interfaces. Okay, now in the next 10 minutes or so, I am going to talk about rate of nucleation. Okay. See, remember how fast the nucleation happens, that will dictate how far the transformation will take place. So, fastness depends on the rate of nucleation. That means, if I have a ice and I want to I put it in deep freezer, I would like it to be frozen in say couple of hours. That is what we observe really. So, that is what I am talking about it. How fast something can solidify depends on the nucleation rate. Obviously, it will also depends on the growth rate, but nucleation rate is the first and foremost important things in doing that. How do we actually discuss that? That is there in the book in a very detailed manner, but I am not going to discuss in a very detailed manner because it is not possible. Actually, frankly speaking, how the nucleation actually happens in the liquid. If I have a liquid, again I am considering liquid because that is easy. There are atoms in the whole liquid, okay, and whenever few atoms comes together, they form a, that I have given you in the last lecture, they form a cluster, and then these clusters join together like this, or they can join in many other configuration, they can join like that also. In many ways, and then become a critical size nucleus. Okay. So, therefore, specifically if I want to calculate rate, I need to calculate how these clusters are joining. Suppose I have a monoatomic clusters, monoatom means single atom initially, two monoatomic clusters join together form a biatomic cluster, and I should need to know the rate of this reaction. That is, suppose rate of this reaction is, forward reaction is R1 and R2, okay, is the backward reactions. So, therefore, the resultant of that will tell me what is the, how many of these clusters with two atoms will form. Similarly, S2 plus S1 can lead to S3, S3 plus S1 can lead to S4, or S3 plus S2 can lead to S5, and each of this reaction will have reaction constant so similarly so on I can write down, and if my critical size nucleus contains n plus 1 atoms, suppose, that means Sn plus S1 giving to Sn plus 1. Finally, if I want to calculate rate of this nucleation, I need to consider a complete chain from this to this, but that is very cumbersome job. That can be done actually, that is people have done, and as a part of many of the certification courses I will to teach it, but we are not going to discuss that in the literature in the class. That is going to take a lot of time, and also it requires many mathematical approaches to be discussed. Okay, so simplicity, let me just tell you that suppose I have liquid, okay, again here liquid, and I have C0 atoms per unit volume, right? Yes, I think it should be per unit volume. Yes, okay. Now, what is the probability that this critical size nucleus that we have seen R star, number of nucleus or number of clusters of R star, okay, will be formed. That probability is equal to, obviously this is must be equal to must be proportional to that, but it will also must be proportional to C0, because initial number of clusters, initial number of atoms are the ones which will start the reactions. I have given you the reaction chain, right. The first and foremost thing is S1 plus S2, S1 plus S1 going to S2. So, S1 is nothing but number of monoatomic clusters, that means number of atoms present in the liquid. So, that is the factor. Now, obviously, if I want to make a nucleus, I need to add only one extra atom, right. If I, the moment R star become R star plus 1, okay, then it has become a complete, it is a nucleus, it is no longer an embryo. I have given you that in the last class. So, because so that to happen, I need to add only one atom, and this addition will depends upon the frequency, okay, frequency of vibrations or frequency of collision, right. So, I can write down that the homogeneous nucleation rate is basically is equal to f C0 exponential minus delta G star by kT. That f is that frequency, vibration frequency, collision frequency, you can talk many things. It depends on vibration frequency, it depends on the activation energy also, because atoms from the liquid are going to join the solids. So, therefore, they need to cross an activation barrier. That why they need to cross activation? Because remember, in the liquids atoms will have certain potential, because liquids atoms are like random, they are moving. So, therefore, there is a definite interaction between them, and the interaction is defined as a potential. Potential means potential well, we can actually draw the energy, the potential energy is a function of distance. So, there will be a potential well, that potential will tell you the potential energy. On the other hand, solid, this is different, right. The interaction between the atoms are more stronger, and they are actually nicely present in this solid lattice. Because of that, the solid atoms in the solid will have a different potential, and these potential differences will be a reason for activation energy. Okay, that potential difference the atom has to cross over to reach from a liquid to a solid. So, therefore, f, this frequency is most of a strong function of the activation available, activation requires, and activation basically comes from the thermal energy part. The thermal energy is what is providing it is the energy to cross over that activation potential. So, therefore, S depends on, F depends on these aspects, these two aspects, the initial the vibration frequency of the atoms and the activation barrier. Now, as you know, delta G star I also know. So, therefore, I can write down this one equal to C0 exponential minus A by delta T square or delta T, let me see, it will be delta T square, it looks like, yes, this delta T square, because delta G star we have seen is 16 pi gamma SLQ 3, this is Tm square 1 by T delta T square into LV square. So, that is why actually it is, this is, so the A is nothing but this term. So, simply I can write down A is nothing but A is equal to this. As you clearly see that homogeneous nucleation rate is a strong function of undercooling. Again, higher the undercooling, higher is the nucleation rate. That is because this is in the exponential term. This is basically very funny things. F and C0 are constant most of the cases, we assume. Okay. They are not dependent on the undercooling, although they will be actually actual sense, but we assume for the sake of this is a pre-exponential term. In the books you will find many of the simple books, this is a pre-exponential term, is a value of 10 to the power 38, 39 or 40. On the other hand, this term which is exponential term has a minus inside the exponential factor, and A is a constant. Why? Because gamma SL is a constant, Tm melt temperature is a constant, latent heat is a constant. So, therefore, it is basically a constant divided by delta t square, and that is nothing but a funny function. If I plot that, so if I plot n homogeneous homo versus delta t, there will be no nucleation below a certain value, and above this value this explosion of nucleation will happen. Why? Because this exponential term looks like this, because this is a minus, remember, because it is a minus, there is an explosion of nucleation, and within a small window of delta t, all that nucleation will happen in the liquid. Okay. So, that is what is how the nucleation rate will depend on the undercooling. So, virtually, if I will continue discussion further in the next lecture also about the heterogeneous nucleation, where we will bring in more concepts so that you understand things better and clearly. In phase transformation, whether it is a liquid to solid, solid to solid or vapor to solid, important aspects in nucleation and growth, especially in nucleation, is the undercooling. Level of undercooling is what dictates the available energies to for the system to transformation, for transformation. Okay. So, that means what? That means all the mathematical formalism which you have seen so far, equations, they are strongly dependent on delta t, either directly proportional to delta t or inversely proportional to delta t, or is inversely proportional to delta t square. You have seen that. That is mainly because delta t actually plays, delta t provides us the driving force or the force for the transformation, a force for the atoms to transform from one parent phase to a product phase. That is why. And we can actually bring in different levels of mathematical concepts to make you understand how actually all these transformations actually happen, all these nucleation happens in different way. So, homogeneous nucleation, as I said, is an ideal situation. Ideal situation means what? It does not actually happen in the real sense, and that is why we always want to know, or eagerly would like to know what happens in heterogeneous nucleation, because that is more close to the real problems. In reality, we always solidify a liquid in a container, and container walls will have certain amount of impurities present, either in terms of oxides or in terms of a gas bubble or in terms of even a pure surface, like say if it is a cast iron mold, there will be not much oxide, but there will be a solid surface, but they will all act as a nucleant that may help in nucleation process, and all this formalism needs to be then modified. But to modify these, we need to have a basic fundamental very clear, and that is the reason in the books or even lectures we always start with the homogeneous nucleation and explain all these phenomena in a manner so that you understand, and it helps also for the both you and also instructor to develop the theory in a rigorous manner. So, we will see in the next class how we can deal with heterogeneous nucleation.